This is exercise for regularization with hotel customers dataset. As you can see over here, we have imported these main libraries which are pandas, numpy and matplotlib. Uh, these libraries are necessary libraries for data manipulation, numerical operations and plotting. Pandas for data handling, numpy for numerical operations and matplotlib.pyplot for data visualization. Apart from that, we have also imported those other modules which are from scikit-learn. So those modules are very important for regularization and evaluation. Let's begin with our first question, which is we have to import the data and drop missing observations. So firstly, we have to import the dataset and we can do it with the help of .read_csv function. So what we will do is we'll use pandas.read_csv function to import a CSV file named hotelcustomers.csv, and using this library, the contents of CSV file are loaded into data frame object named df. After that, what we are doing over here is we are using .set option function. So this will be used to display all the columns. As you can see over here, display.max columns is set to none, which ensures that all columns are shown even if there are many columns in dataset. And df.shape prints the shape of the data frame, whereas df.head displays first few rows of data frame. So we can see over here df.head has printed first few rows of our data set, and over here the df.shape has printed some values. So let's begin with our next goal, which is we have to drop missing observations. So we are going to use .drop NA function over here, which removes any rows with missing values. In place equals true. There must be equal over here. In place equals true. Parameter ensures that the data frame is modified in place, meaning the changes are applied directly to df rather than creating a new data frame. And over here .shape and .head does the same thing which it did in our previous example. So df.head has printed over here few columns, few rows, and all the columns are printed. And as you can see, df.shape has printed some values over here. So our next question will be we have to encode categorical variables and create dummies. So for this we will be using the pandas.getDummies function. So this function is used to convert categorical variables into dummy variables. We have passed df data frame as input to this function, and drop_first is assigned value true, and it is a parameter which is used to remove first category of each categorical variable to avoid collinearity issues in the resulting dataset. So original categorical variables are dropped and the encoded dummy variables are added to the data frame. And df.head prints few rows, as you can see over here. We can see over here we can't actually view nationality column in this data frame. So what is happening is each value of this each variables of the nationality column has prepended with nationality, and it is displayed over here for each of the countries. So as we can see, nationality_ASM, nationality_AUT. This is how all the variables from nationality column are now created as a column with prepended name of nationality. And this is how we have created our dummies in our question 2. Let's move on to question 3. Here we have to create revenue by adding lodging revenue and other revenue. Drop customers with zero revenue, drop lodging revenue, other revenue. So over here what we have to do is firstly by using this code of line, what we will do is we will create a new column rev, as you can see over here. So rev in the data frame df, this column is obtained by adding corresponding values of lodging revenue and other revenue. This step calculates total revenue by combining the revenue of lodging and other resources. After this, on line 2, this line creates a new data frame df1 by selecting only the rows from df where the value in the rev column is greater than 0. It effectively filters out the customers with zero revenue. And on the next line over here, this drops the columns lodging revenue and other revenue from the data frame df1. The drop function is used with the axis is equals 1 parameter to indicate that columns should be dropped rather than rows. So axis equals to 1 represents column wise. And dot shape and dot describe function is used to compute descriptive statistics for the rev column in the data frame df1. It provides information such as count, mean, standard deviation, minimum quartiles, maximum values of the rev column. This helps in understanding the statistical properties of the total revenue variable. And dot shape brings the shape of the data frame. Now let's move on to our next question. In this question, we have to define y and x. We have to standardize numerical predictors, but we do not have to standardize categorical predictors. So firstly, what we will do is we will use dot describe function, which will provide us a summary of statistical properties of the numerical columns in the data frame df1. So as you can see, count, mean, standard deviation, you can view everything for our data frame df1. Now, next what we will do is we will start writing our code for y and x. So these lines define the target variable y and predictor variables x. Target variable y is assigned values from the rev column of the data frame df1. The predictor variables x are obtained by dropping the rev column from df1 using drop function with axis equals to 1 parameter, including that column should be dropped. Later on, x.shape prints the shape of the data frame x, and second line over here dot head displays first few rows of the data frame x. As you can see over here, this is the shape of our data frame x, and this is the table for x, which is printed using x.head. Moving on, now we are asked to separate numerical and categorical predictors. So for doing that, we have written following code. So this code separates the numerical predictors from the data frame x. The variable x underscore num is assigned the columns from index 0 to 9, as you can see over here. From 0 to end variable is 10, but we don't consider that end. So we have to consider from 0 to 9. That would be 10 columns. Using the ILOC indexer. It creates a new data frame containing only numerical predictors. The second line over here displays first few rows of x underscore num data frame. So this over here are numerical predictors, as you can see. Let's move on to categorical predictors. Over here we have written some code for defining categorical predictors. So the variable x underscore cat is assigned the columns from index 10 onwards. As we can see, end variable is not written, so it will go until the end of it, indicating all the remaining columns after the numerical predictors. It creates a new data frame containing only categorical predictors. So once we have defined all the numerical predictors and categorical predictors, let's move on to standardizing numerical predictors, as we are asked over here to standardize numerical predictors. We'll perform this operation now. Yes. So over here, this line of code standardizes the numerical data, which involves scaling the values to have zero mean and unit variance. The dot fit transformation is used to fit the scalar to the data x underscore num and then transform it. Type function is used to return the type of the variable x underscore num underscore std. So we get numpy dot n dimensional array over here as our output, which is the type of this variable. Later on, we have to concatenate numerical predictors and categorical predictors. And over here, we will use standardized numerical predictors and non-standardized categorical predictors as we were asked to perform it. So this dot concat function is used to concatenate standardized numerical data and categorical data, and is performed along the columns as x is equals to 1 is used over here. And again, type of this variable would be numpy dot n dimensional array. Moving on to our next question. Let's move on to our next question. Over here, what we have to do is we have to run ridge regression using standardized predictors. We can use shrinkage parameter 1 to 200 step equals 10. So plot the estimated coefficients as a function of the shrinkage parameter. So over here we can see some information regarding range function and a range function, how it works. So important thing over here is start parameter will be inclusive and stop will be exclusive. So we don't have to consider the stop parameter when we are performing any operations. Range function will only take integers as parameters, and we can work with integers only in range function, whereas in a range function we can also use floating number as well. Moving on to our code, over here we can see we are using a range function over here. So how it works is this line creates an array A using a range function from numpy. It starts from 1 and increments up by 10 until it reaches 200. So this will be range or shrinkage parameter values for ridge regression. Now over here, what we can say is this line initialize an instance of ridge regression model M2 from scikit-learn and creates an empty list to store the estimated coefficients for each shrinkage parameter. Let's learn how this loop works over here. So this loop a loop is started where each iteration performs following steps. This loop iterates over each value in the array A, sets the shrinkage parameter alpha of the M2 ridge model, using setParams function. So later on, it fits the model using the standardized predictors x underscore std and target variable y, and then appends to the estimated coefficients to coefficient list over here. Dot shape parameter returns the shape of the coefficient list over here, as we can see in the code. So this is how dot shape function gives us shape of the coefficient list over here. Moving on, now in the next part of the code, what we are trying to do is we have to create a line plot, and we are using dot plot function over here from matplotlib. So plt.plot creates a line plot where a represents the x-axis values and COEF, which is coefficient, represents the y-axis values. Here over here we are labeling our x-axis as alpha, and we are labeling our y-axis as ridge coefficient. The plot visualizes how estimated coefficients change as shrinkage parameter varies. So this will change as shrinkage parameter will vary, and estimated coefficients will move on to different values as we move forward and backward. So moving on to our next question, over here what we have to do is we have to run ridge regression using standardized predictors. Use leave one out cross validation and shrinkage parameter 1 to 200 step equals 10, and we have to report RMSE. So over here, as we can see lines of code, what's happening over here is in this line of code, it creates an instance of the reach CV regression model M2 from scikit-learn. It performs a ridge regression with cross validation to select best shrinkage parameter from a specified range A. The alphas parameter is set to A to and store underscore CV underscore values is set to true to store the cross validated predicted values for each alpha. The model is fitted. As you can see over here, dot fit function is used. The model is fitted using standardized predictors x underscore std and target variable y. Over here in this line of code, the line here calculates the mean squared error of the best performing model from cross validation by retrieving the negative of the best score from M2 and assigning it to MSE2. And over here we have written this to output the value of MSE2. As we can see over here, this is the value of MSE2. This line of code, what it does is it retrieves the shape of the cross-validated predicted values stored in m2.cv underscore values underscore. So we can see the values right over here, and over here RMSA2, it is assigned to numpy dot square root of MSA2. So what's happening is this line of code calculates the root mean squared error RMSE by taking square root of MSE2, and we have printed over here the value of RMSE2. Let's move on to our next question, which is we have to run the lasso regression using standardized predictors. We can use 5-fold cross validation. Later on we have to report RMSE for the best model. This is our main target for here. So as we can see over here, we have written a code over here for lasso linear model with iterative fitting along a regularization path. So what's exactly happening over here is an instance of lasso CV regression model is created. It performs lasso regression with iterative fitting along a regularization path. The model automatically determines the optimal alpha by using cross-validation. The model is fitted using standardized predictors and target variable y. Default number of alphas over here is set to 100 and default number of folds for cross-validation is set to 5. Moving on, over here we are trying to print shape of our M3.alphas. So this indicates number of alphas available in the regularization path, and the displayed alphas provide a subset of the values used in fitting the model. And this line of code retrieves and prints the first 20 alpha values from the alphas. And later on we have printed the value of m3.alpha underscore right over here. This is the optimal value of penalization chosen by cross validation. So m3.alpha underscore retrieves the optimal value of penalization parameter chosen by cross validation. It represents the best alpha selected by lasso CV model. Later on, what we are doing is we are trying to print the shape of this variable MSC underscore path attribute of M3, and this line of code retrieves and prints mean squared error MSC values from the MSC underscore path underscore attribute of M3 for the first 5 cross validation folds and all alpha values, as you can see over here. This is the shape of MSC underscore path underscore, and these are the array values of MSC underscore path underscore. Moving on, we are trying to find the index of optimal alpha in this part of code. So firstly, what we will do is we will assign the array of alpha values from the lasso CV model M3 to the variable ALP, and we will try to convert it to list using .toList function. And if we have to check the length of alp underscore list, we can use length function, and as we can see its length is 100. Later on, over here .index function finds the index of optimal alpha value in ALP underscore list, and we have assigned this value to best underscore index, and best underscore index is printed over here. In the same way, we have to find MSCs corresponding to the optimal alpha values. So we have used this line of code which retrieves the mean squared error value from MSC underscore path underscore attribute of the lasso CV model M3 at the index best underscore index, and MSC3 is written over here to print the value of MSC3. This is the output of value of MSC3. So as written over here, MSC3 represents the best MSC corresponding to the optimal alpha. And at last, what we are doing over here is we are using numpy.square root function, and we are using it over MSC3 value. What we have to do is we have to take the square root of the mean. So firstly we will do a mean function on the MSC3, and we will use dot square root function on it to get root mean squared error for dataset. And RMSE3 over here displays the calculated value of RMSE. We have one additional exercise over here which is optional. So what we have to do over here is we have to count the number of non-zero coefficients from the lasso regression. So hint over here is we can use coefficient underscore dot non-zero function. So what we can do is we can use dot non-zero function over here to get our result. So starting with our first two lines of code, what we are trying to do over here is we are trying to print the length of the uh, variable over here, and this attribute which represents the coefficients obtained from the lasso CV model M3. It indicates total number of coefficients in the model. Additionally, it displays the first 20 coefficients from the from this attribute itself. Next, what we are trying to do is in those lines of code, what we have to do is we have to print the length of the variable firstly, and we have to display the indices of non-zero elements in the coefficients. So this dot non-zero function returns tuple of arrays where each array contains indices of non-zero elements. The length represents the number of arrays in the tuple, which indicates the number of non-zero coefficients. In this case, there are 58 combined as one. Moving on over here, this lines of code uh, prints the type of the attribute and type of the non-zero result as well. So over here, as you can see, it's n-dimensional array. This m3.coef coefficient underscore attribute is numpy.n-dimensional array. It belongs to that class, and this dot non-zero function which we have applied to it, it results into a tuple. So m3 dot coefficient is a numpy array, and m3 dot coefficient dot non-zero function is a tuple. So at last, what's going on is the this line over here, it prints the length of this function. So this line retrieves the length of first element. As we can see inside this index, 0 is written, which is the first element. So it is the first element of this attribute, which is resultant of this function, and it's a tuple as we have seen over here. And the result of it is 24 as its length is 24. And at last, what we are trying to do is we are trying to print uh, a statement over here. So what's going on is this line prints a formatted string that provides information about the number of coefficients and number of non-zero coefficients in the model. It uses format method to replace the braces placeholder, braces placeholder with the respective values obtained from length of M3 coefficient, as you can see over here, which is total coefficients, and over here, as we can see, it is non-zero coefficients. So by executing this code, we will obtain information about number of non-zero coefficients in the lasso regression model. It helps to understand the level of sparsity or feature selection achieved by the lasso regression. So as we can see over here, out of 215 coefficients, 24 are non-zero.